And also Professor Anup has worked at IMEC, which is one of the leading semiconductor consortiums in Belgium. I also spent some time there long time ago, and then he worked on neuromorphic computing over there and has many collaborations across the world building these neuromorphic computers. And so without much delay, I'd like to welcome him to our lab, and please ask a lot of questions. We're here to learn. Nobody's assuming you know everything. Ask silly questions, stupid questions, but ask. Welcome, Anup.
Thank you so much, Rahul. Rahul, if I may ask you, I can get a question.
Yeah, sure.
And now this one. Okay, thank you so much for attending my talk. And once Rahul is back, thank you, Rahul, for the nice introduction. So what I will do today is, in my talk, I'll explain some of the research that I am doing at Drexel, either in our group or also in collaboration with different other companies that we are working on and different other universities that we collaborate with on this topic. So what I would say is that a key takeaway from this from my talk would be that there are certain ways that you can design your algorithm and your hardware, which will be helpful to minimize energy consumption in certain cases. And in general, you'll see that there is a different way to build systems that are more intelligent, more energy efficient, and still perform more or less the same kind of accuracy, you could say, or performance as compared to some of the traditional work. So at Drexel, I'll give a quick background. At Drexel, I direct something called the DISCO Lab, which stands for Distributed Intelligent and Scalable Computing. Most of our research are geared towards neuromorphic computing, but there are a whole group of students who are working on memory technologies, specifically on in-memory computing, in-memory data compressions, and stuff like that. But today I will not talk too much into that. I will mostly focus on neuromorphic computing. My research area, if you look at, so there are three key research areas that I lead. One of them is neuromorphic algorithms and architecture exploration. And I will explain what neuromorphic algorithms and architectures are. And then I build something called the hardware-software interface, such as so that even if you build a system, how do we make it more efficient for people who don't know how the hardware works, can run their program on it, right? So think about it, computers in 40 years ago. Those computers need to be hand programmed to do any kind of computations. But today, thanks to Microsoft, although many of us don't like Microsoft, but thanks to Microsoft, the interface has become so smooth that you can easily write your own code and run it. And later on, it was picked up by Linux and all those new type of operating systems developed. So we are actually building something like that, which is the system software or the operating system like framework for neuromorphic hardware to make the hardware abstracted away from the programmer or application developer, so that you don't need to worry about how to program such a system. It doesn't look like an Intel core inside. It is a very different kind of system. But what I hope to build is something that can help you to run your code without knowing exactly what happens underneath. And finally, what I also work on is something called dependability and security. So I can give you a little bit overview of it during my talk, where I'll show that neuromorphic hardwares also lead to a lot of security problems and a lot of dependability problems. And think about it, this type of systems going into autonomous cars, or for example, cyber physical systems, healthcare domain, security is a big problem. And so is dependability. If one of the neural networks that you are running on the hardware, any neuron becomes faulty, the actions will be catastrophic in some cases, right? And dependability aspects is something that I deal with in the lab, although it's a huge topic in itself, and I will again restrict myself today to only algorithms and architectures and the hardware software co-design. So overall, this is a kind of high-level overview of how my different research areas integrate towards at a high level. My goal is to make intelligent IoTs or Internet of Things, which can be used for environmental monitoring, autonomous systems, or even healthcare. But to do that, what we have to do is something called full stack co-design, where, of course, many of you already know that Internet of Things have different hardware stacks, from sensors to edge to cloud. For each of these stacks, you can do a co-design where you can do the algorithm and the hardware development simultaneously, so that every stack is efficient. So instead of tackling the problem at a global scale, you tackle the problem at every stack. You make the sensors intelligent, you make the edge computing intelligent, and you make the cloud computing intelligent. And that's why we build intelligent IoTs. So this is kind of what I do. And now what I will do is I will go deeper into the first two areas, which is algorithm and architecture exploration and the hardware software co-design. I'll leave the dependability topic for some other time, so that you don't get too much defocus from the basic concepts that I'm going to introduce today. Okay, so this is going to be the outline of my talk. So I will introduce you to spiking neural networks. Now, this might sound something a little bit new to many of you, but I will try my best to give you an idea of how spiking neural network works. Then I will show you how the hardware for such an architecture or such a machine learning algorithm looks like, and then talk about the hardware software or the system software, which is basically compilers and runtime, and finally some idea of how we can do a hardware software co-design to build efficient neuromorphic hardware. So I want to also give you start with a brief history of neural network, actually, because when I go and start talking about spiking neural networks, many of the comments I heard are that these are very new type of machine learning models. We don't know about so much. We only talk about deep learning and all. But if we look at the history, I will show you that the roots of spiking neural networks are formed exactly at the same time almost, when normal neural networks or artificial neural networks came in. So you all probably know the 1943 Macaulay and Pitts model of basically a simple neural network using electrical circuits, which actually form the pathway to artificial neural network. So you can essentially call 1943 is the statewise time when first neural network came into picture, right? But very soon, so this is how neural networks at that time look like. You have a neuron, which is now a neuron, and you have two inputs, and you compute some output. But very soon, in 1949, Donald Hebb actually wrote a paper called The Organization of Behavior. And there he described certain principles from the brain that today forms the pathway to spiking neural networks. So even though spiking neural networks may be thought about as a newer concept, it has its roots long back. It didn't come out into light so much. And I will explain why in the next few slides. But it used to be around the same time when both the artificial neural networks and the spiking neural networks came into. So then, of course, we all know there were quite some development happened, and one of the most prominent development was when Rosenthal proposed the perceptron model. But those perceptron models are simple input-output relationship. And as we all know, in 1969, Minsky and Papert proposed the famous paper where they showed that you cannot really train a perceptron model without going into the infinite number of iterations required. So if you are with the limited resources, limited amount of time, you will never be able to successfully train a perceptron model. And that is actually what led to something called the AI winter. And most of you probably know the AI winter, which is 10 to 12 years where there was not much research on neural networks. And that was mainly triggered by this 1969 work from Minsky and Papert. But still, during this time, a lot of other developments happened in parallel, didn't come into so much prominence, but it still had some work went on. And one of the prominent work is the backpropagation of error, which is a PhD thesis in 1974. So that was one of the most prominent work that happened in AI winter, although it was not so much, it didn't come into prominence so much at that time, but there was a there was the PhD thesis in 1974 on backpropagation. And then we all know that in 1982, Hoffield started with the Hoffield network, which was presented at the National Academy of Science, and followed by 1986, famous backpropagation rediscovery by Rumelhart and Hinton. So these are all the things that happened during the deep learning era. And 1990 was the CNN, first CNN, where it showed that gradient-based learning can be applied to document recognitions, and that actually started everything with AlexNet and these are all the new models that you are used to seeing, the state-of-the-art models. And then, yeah, 2022, it carried on all the way until 2022 for different types of accuracy. So these are all the works that are going on in CNNs, but at the same time, SNNs were also started developing, although it was not picked up by many because primarily the way it works is slightly different than a conventional CNNs. And it was a little bit difficult to train SNNs, and I was speaking today about this, is that all this backpropagation, which basically was the driving force for many of these CNN models, couldn't train a spiking neural network. And the reason why it couldn't train a spiking neural network is that for backpropagation to work, it needs a function to be differentiable. That means you need to find a differentiation of the function at every point in time. That means the function has to be continuous in time. And spiking neural networks are non-continuous, predominantly are event-driven. That means it has a spike, and then there is absolutely no activity for a long time. And that's why spiking neural networks couldn't be trained so easily using backpropagation. People left off and said that, let's leave it out. Let's focus on CNN for now. So if you look at the generations of neural network, mostly the first generations, which are the basic ones based on perceptrons, threshold gates, and used for linearly separable inputs. But after the winter, AI winter, came the second generation, which is where you are using a lot of activation function. Several different architectures came into play. CNN is the most prominent one, but there was also recurrent neural networks, MLPs, and deep belief networks. And finally, the third generation, which employs spiking neurons, or sometimes referred to as integrate and fire neurons. And I will explain the concept of integrate and fire neuron in the next few slides. So these first two generations are typically the generation of artificial neural network, whereas the last is the generation of something called the spiking neural network. As I said, although this is the third generation, so you might think this is a very new concept, it has its roots almost at the same time when artificial neural network was formed. So in the next few slides, what I will be doing is I'll give you an outlook of SNN. I will talk about learning mechanisms, inferences that are being, how spiking neural network are used for inferences, some on-chip learning, which is a very new concept, or not exactly a very new concept, but rediscovered concept that has been quite important in today's AI systems. And then finally, some applications before moving on into the hardware part of the talk. So one of the key distinction between spiking neural networks and convolutional neural network is something called the activation. Instead of an activation function, you have something called leaky integrate and fire. A neurons that has something called membrane potential. That means it has a membrane voltage. And as you put current into it, the membrane voltage increases. So you can see over here, the membrane voltage is increasing. And when there is no spike, it decreases. So it's a kind of like a capacitor behavior. If you put a charge into it, its charge increases. And then if you don't do anything, the charge gradually reduces. So it's a kind of a capacitive behavior that you can see that the
how does the charge decrease there?
So if you don't do anything, this capacitor will lose charge over time.
So the VTH is a resistor?
No, this is a threshold voltage, and I will come to that.
Then how does it?
So you have a current that is flowing charge into this capacitor.
Yeah.
If the current is not there, the capacitor will discharge, right?
Yeah.
Capacitor will lose charge. Capacitor cannot hold charge for a long time.
I don't see how you lose charge there.
A capacitor as a fundamental capacitor, it's a two-plate, right? Capacitor is a two-plate. and you have the charge inside it.
Mhm.
And if you don't do anything, it will lose charge from the leak paths
Okay.
surrounding. So all the leak paths will be formed and the charge will start losing. This is not anything. This is just a threshold voltage I'm representing. So you see it's increasing, and if there is no spike, it will decrease. So it keeps on increasing and decreasing. If there is a spike, it increases. If there is no spike, it will decrease. And once it crosses this threshold, which is represented as VTH over here, a spike will be generated. Okay. And so here in this diagram, you can see that the membrane potential is varying according to how the input is provided, although I'm not showing the input area here. But at certain instances, it crosses this threshold, and those are the instances where a spike is generated. So basically, this is how your spiking neural network works. This membrane voltage is inside the neuron. So the neuron is having something called the membrane voltage, where its potential increases and decreases based on whether you have spikes or not. And whenever it crosses a threshold, it will emit spikes that you can see over here. Yes.
But the graph doesn't look like that. The graph it's a exponential, like it's very slow decay on a discharge, right? When it's a super fast charge when it's a
That is because the leak paths are not that resistant to immediately charge down. So there are a lot of other flavors. So this is integrate and fire. That means it will integrate charge, and then when the charge crosses a threshold, it will fire it. The leak part is basically something called leaky integrate and fire, and I'm showing here a leaky integrate and fire. Now that leak rate varies from implementation to implementation. Some implementation instantaneously drop the threshold. Some implementation slowly decays it.
Is there a hyperparameter used in the training?
Think of it as the resistance value. If the resistance is low, it will discharge very fast.
yeah, that's just like a simplified.
Yes, this is a simplified just for understanding purposes, and I'll show the detailed architecture of a neuron later on. There are a lot of hyperparameters used. For example, the threshold voltage, VTH.
Yeah.
Plus, there are other things. For example, once there are actually this logic is not this simply as a box. It has a lot of insight. For example, once you fire, you cannot fire another spike within a certain interval.
Yeah.
Okay, and
what is that called? There's a name for it in cell biology. It's the
Hold on, time.
refractory period.
yeah, that is the refractory period where you just wait for a certain amount of time before you can fire. Even if your potential is still higher than the threshold, you cannot fire a second spike.
Right.
You have to wait for a certain amount of time, and that is defined by the refractory period. And that all those things are implemented in this logic.
I see. Okay. So
And when you are dropping, for example, how much can you drop? Right, that is called the resting potential. So
right.
you have a potential until when you can drop. Beyond that, it will not drop. So now how you drop is the resistance value.
So here you're plotting the membrane potential. Is the membrane potential on the diagram? It's the capacitor.
No, it's the
voltage?
voltage across the
Okay,
capacitor.
got it. So then your U of T, what does that look
That
like?
is the image.
Okay.
And
So
how does that look like? Exactly like this.
okay,
Because
so that's
think
also
about
a
it.
spike.
This is the neuron that is generating spike, but the neuron is also receiving spike.
Got
So a spike like this is coming over here.
Okay, so everything's a spike.
Everything is spike. The
And then-
only linear thing inside, or only continuous time thing inside, is the voltage, but that is internal to the neuron. You cannot
Right, you have to integrate with it.
exactly.
When it comes to the model you've shown on the left, is that actually an accurate, is that just something you put there so it's easier for us to understand?
This is the model that was proposed in 1949.
Okay, so that is the actual, that is the representation.
That is the representation. Now, Carver Mayad, and I will show you later, Carver Mayad, who is a professor, who is still a professor at Caltech. He proposed concept of neuromorphic computing, which is the electronic circuit. But his circuit of neuron differs very differently from what you see. This is the conceptual picture that was proposed, but later on this picture became something else.
Okay,
But
but it got more complicated or
it's
less?
way more complicated than
Okay.
but this is just a representation, complex representation of, or simplified representation of your neuron.
Got it.
So yeah, so this is, so you don't have a activation functions like a separate functions, any type of functions, you forget it, those are not existent in you.
Yeah.
All it exists is a neuron that receive spikes generate spikes. And whenever the receive spikes, all spikes are something like this. Yes.
So there's no variation in magnitude of these spikes. They're all the same size.
Spikes by definition is a direct delta function.
Okay, so, okay, got it.
Okay. Any other questions? So now then,
Yeah, what does a direct delta function mean?
oh, it's a function shape that has infinitesimally small duration, and the peak is extremely high.
Okay.
Basically. Yeah. So basically, within a small delta t, it has existence. Beyond that, it doesn't have any
Okay.
existence. Okay, so this is one concept. Now, why the complications start coming in? Because of the way how you encode information. This is a simple, you have an input, your membrane voltage is increasing and decreasing, and then once it crosses a threshold, it spikes generated. That is all good. But you have to also think about how do you encode information, physical information. For example, you are sensing something from a sensor, right? How do you represent that in form of a spike? So there are different ways to represent spikes. And what I'm showing over here are three most popular ways to represent information in your spiking neural network. The first is called rate coding. So here what happens is that, think about it in your convolution neural network value. It's a value of a tensor converted into its spike in the form of a rate. So let's say you have a tensor whose value is 75. So you can think of equivalently, you are generating a spike whose firing rate is 75 hertz or something like that. So basically it's converting a pure value that you obtain into a corresponding rate of spikes. Very simple to implement. You will get extremely good accuracy to it, but too many spikes gets generated, and that consumes a lot of energy. Okay. The second type of coding, and which is called the interspike interval coding. Here, the information is represented by the interval between the spike. So you control the refractory period so that your spike information, any type of information that you are trying to represent, let's say, think about it that you have an image, and when you are presenting an image to a neural network, typically what do? We take pixel by pixel and present it to the neural network, right? So consider this way, that each pixel can be converted either to its value of a pixel can be converted to a spike rate. So that becomes rate coding, or the spikes that are feeding corresponding to a pixel value can have something like the interval between the spikes represents the value of the pixel. Okay, so that becomes interspike interval. And the third one is the time to first spike. Time to first spike is just one spike is generated, and the time when it's generated is roughly proportional to the value of the pixel. So if you have an image with a pixel, the pixel values is what will decide when the neuron will spike. Okay, so these are three different types, and of course, as I said, rate has the highest accuracy because rate coding, it is almost equivalent to talking about analog neural network, because it's nothing. Instead of the analog value, you have rate. Then you have time to first spike, where only one spike is generated. Of course, this will be having the minimum energy, but accuracy is very bad, or not super bad, but more or less much lower than rate. But what is most important, and what is currently the research community focusing on, is the interspike interval, where information is encoded as the time interval between the spikes. And why this is important? Because this lies somewhere between rate and TTFS. So it has a good amount of energy efficiency and a good amount of accuracy. So what we are trying to do right now is move this up into it so that we get a high accuracy as rate, but the energy is much lower.
Why there's an accuracy difference?
Think about it.
There's no information loss, right? When they're encoding.
There is information loss happening because if you have a first spike, time to first spike, only one spike, information, think about it, you have a neuron, only one spike is coming. So you have to do all the processing of the threshold voltage and generate a spike based on only one spike.
Yeah, but you have that one spike time being the correct
value. It is difficult. It is difficult because that's how CNN works, right? CNN, the analog values or the analog tensors are what actually helps to get the accuracy numbers, right? If you convert it directly into spike form, it will always has the similar kind of accuracy as your CNNs. But as you start playing with the different type of encoding, and in this case, the time to first spike, where only one spike is generated, that spike needs to propagate, and I will talk about this. That spike has to propagate a long distance. So what happens is your time is losing, you're losing time. So think about it, 10 spikes coming, okay? You receive it at a later distance, but all the 10 you will be receiving, right? So rate-wise, there is no change. But if you have one spike, the timing, sorry,
the information decreased.
exactly, and that leads to accuracy.
So it's not necessarily that the encoding is lossy, it's that the encoding, when propagated through the spike,
Will lead to
loss.
losses. Yes.
So what are the timescales we are looking at, like in terms of intervals between spiking?
So typically, in biology, most of the sensors, or most of the sensing mechanism, are roughly around hertz processing. So basically, you can think of hertz, this spike frequency are generated to hertz. But somehow, somewhere nowadays, what we are looking at also is kind of a millisecond range. So you can think of these spikes intervals are in the range of milliseconds, because with 1 second is absolutely impossible to do anything real time. So at least have some sense of milliseconds, so that way you can do some amount of process.
But what is the limiting factor of not going faster?
The thing is, these circuits of neuron are too big as compared to analog neurons.
So it's not just a ADC.
Yes, it's not just the ADC, it is each of the circuits are bigger, but they are more efficient when you are running it at a slower rate, so that the energy consumption is lower.
I thought when during I can probably ask a question during implementation, but I also, why do we need an ADC here?
Okay, I'll come to that, because the
You can
fundamental
use
no.
a quantum counter or something.
Yes, but the thing is, the fundamental fabric which communicates is digital, like a network on chip.
Yeah, but if you use like a,
How do you transmit a spike over a network on chip, which is fundamentally digital in nature? I'll come back to it when I talk about the implementation, but it's.
Oh, no, I'm good.
You do. So as I was saying, that the spiking CNNs using spiking neural networks, you can pretty much convert, you can create any type of operations like convolution, pooling, and so on and so forth using leaky integrated and fire neurons. In our previous work, we have actually developed such a model which can convert any CNN models that you give into corresponding spiking versions, where the leaky integrated, where the normal neurons and the activation functions are replaced by, for example, leaky integrated fire neurons. And you can see the accuracies are pretty much comparable, not exactly the same, but most of the application we see that we are pretty much comparable with the actual accuracy obtained on a CNN models. Now, as I was saying earlier, that SNNs are not the best for everything, right? For example, convolution kind of architectures, if you look at, SNNs are not that great in the first place. So if you have an option to use CNNs, please do use CNNs, because accuracy wise, you will never be able to compare with CNNs. Plus, there are a lot of intelligently designed hardwares already in place to accelerate and achieve low power of the CNNs. SNNs are better in certain respects, and we'll talk about that when we discuss it in the next few slides. There are certain scenarios where SNNs outperforms normal analog neural networks. So I'm of the opinion that both are equally good, depends on where you are applying it. So this is just one example where I showed that a CNN can be converted into SNNs, and every type of operations can be converted into an equivalent operation in the spiking domain. So typically what happens, the most of the research that that happens are on goal-oriented machine learning, where you train a CNN on a particular database, because training SNNs is difficult because of the non-continuous signals, where you cannot really differentiate the loss functions. And then what you do is you convert the CNN into, convert the CNN into spiking neural networks. We call it the spiking CNNs or SCNNs. And finally, you map the SCNN to the hardware. So there are different types of hardware that are proposed in literature, and these are some of the example hardwares that are spiking hardware that are proposed, and along with the number of neurons, number of cores, and so on and so forth that you can see in this. So we, together with IMEC, we developed this something called the microbrain, which is shown over on the second column, and I will show some results from there. IBM's is over here, which is IBM's TrueNorth, and Intel is Loihi over here, and then University of Manchester is Spinnaker that you can see over here. So some of the context of where we are going with our research. Yes.
So is this like an ASIC kind of thing where you have a bunch of these neurons or neuron simulators, and you can use software to define how they're connected together, but otherwise you get this big board of like fake neurons?
So basically, usually all these architectures over here come as a neural substrate. It has neurons, it has synapses, implement an algorithm on it.
Okay,
However
so,
you want to do.
so the kind of
Connections are fixed.
okay.
You cannot change the connections at runtime. So you are pretty much limited to the architecture that the hardware comes up.
Okay, so it's an ASIC, not an FPGA.
It is ASIC and FPGA. You can do it on FPGA, and I will show you some results on that. As
Oh,
well.
but I mean, like it's not an FPGA, as in you can't reconfigure it, you can't change the connections.
On runtime, no.
Okay.
But the good part is how neural networks are clustered and how they are mapped. You can implement many different architectures, many different CNNs, skip connections, everything you can implement on those hardware.
Okay.
Even though the actual static hardware doesn't support it, and that's where I was coming to.
Yeah.
You have cores where you have, it's just like in biology. So in biology, if you look at, there are something called local and global synapses. So local synapses are local connectivity where you have dense connections, and then you have global synapses, which are long distance synapses, which are not so heavily connected.
Right. So the
So-
global ones you can reconnect.
Exactly. So global ones are typically implemented as a time shared, time multiplexed interconnect. So you can pretty much transfer anything, and with a small information on which neuron it should go to, you should be able to do it.
Okay.
It's not like physically placing the neurons, it's generating something from the local connections and telling it which other neuron in which other core you have to transmit it.
Okay.
And that transmit mechanism is digital. And that's why you have to need a ADC, analog to digital converter. Plus you need certain other converter, and I will talk about that later on. So, so that is mostly on the inference, not.
Before you, so what is the example that the SNN is better than the other hardware?
Is the next few slides.
Okay.
So, so let's now look at something called on-chip learning, which is also a very interesting concept, and it has been proposed long time back. So this is the emerging area, and this is one of the area where spiking neural network outperforms most of the conventional analog neural networks. Think about it. You have a neural network which has been trained on a huge amount of resources like a GPU, and you map it onto an edge device. If you have to retrain anything, can you imagine? You cannot do it on the edge device. You have to pull back the network, retrain it, deploy the network again. That's where spiking neural networks comes into extremely important. It can do extremely low power on-chip learning. So as and when new events are being discovered, it can learn, the architecture can learn, and you have certain algorithms for that. So, so in those cases, what you do is you start with an SNN architecture, and then what you can do is the connection between the neurons are updated based on the spike timing between the pre and the postsynaptic neuron. So this is something called the spike timing dependent plasticity, which is a form of Hebbian learning. And we saw that Hebbian learning in 1949 paper. And this is a completely unsupervised learning algorithm that SNN supports. So it observes events, and based on that, the weights between the neurons automatically adjust based on what events you are looking at. So it's a complete unsupervised learning where the weights are getting trained just by looking at what events or looking at the events that you are perceiving into the architecture.
So is this like the fire together, wire together?
Yes,
paradigm?
this is those which fire together, wire together.
Is there a number of neurons that are present on each chip?
Yes, so I mentioned that the chip capacity, let's see. If I can.
Neurons are mapped to cores, and then there are.
So you have neurons per core, number of synapses per core, and then number of cores per chip, chips per board, and finally
Well,
it's a hierarchical architecture that that is proposed.
So is the to come up with a SNN design, you
Right.
always convert from some ANN or CNN
No,
to SNN?
that is for inference only. Let's say you have CNN type of architecture, then you convert it into SNNs. First you train it, and then you convert it into SNN, deploy it on those kind of hardwares. But this capacity, these are all new capacity that SNNs facilitate, which CNN doesn't. CNN, you have to learn it from scratch. Here, what happens is, let's say you have a new event that you saw. The architecture itself will adapt to that new event, which has been not seen before. So this is kind of the
So you
whole
have
thing.
this unsupervised learner, but in hardware.
Exactly.
So you mentioned that the architecture itself will change. Will you be able to remap like the core structure? Can you?
No, the core structures remains the same. So what happens is the weights. So basically, we'll talk about that.
Okay,
so what
it's like
happens is
iterative retraining, but not like
the
module, like will the architecture?
the
itself-
architecture will not change.
Oh, okay.
What will change is the synaptic weights or synaptic connections. So basically, the number of spikes you can think of, number of spikes going from one neuron to another will change. Was there a question? Okay, so this is the basically some a little bit of more mathematics into how the weight changes happen. So basically, based on whether the presynaptic neurons fires before postsynaptic neurons or a spike is coming after postsynaptic neuron, you have different weight dynamics. So basically, imagine that you have programmed a certain amount of weight to start with, and as the event is coming, and that event has not been seen before, the weights can change actually from its own value, and that weight change will result in more spikes to be more spikes to go or less spikes to go between neurons, and that will help in facilitating the new form of learning. So in general, if you look at the total space of learning algorithms for spiking neural networks, you have a supervised learning, which is backpropagation based, but usually backpropagation through time, and you limit it for a very small time interval. Again, as I said, that spiking neural networks are predominantly non-continuous. So what you have to do is you have to consider a very small time interval where it is continuous, differentiate it, and then leave it like that. So you have to zoom the timing into a very small portion to calculate the error derivatives. Then there is something very interesting algorithm that we have proposed in the recent days, which is called force. And I will talk a little bit about that later on, which is a supervised learning algorithm, but a kind of alternative to backpropagation. And then on the unsupervised learning, there is a whole different type of unsupervised learning mechanisms. For example, spike timing dependent plasticity is the heavier learning rules, but there are also short-term plasticity, long-term plasticity, plus there is something called neuromodulations. And I was speaking to one of the students here that neuromodulation is where we look at a pattern and then we try to complete that pattern. So basically it's a pattern completion step, and spiking neural networks are very good at it. So you show a partial pattern to the neural network, it should be able to find out what is the true pattern is. And that is done through something called neuromodulation in human brain. So we have a similar algorithm for spiking neural networks on neuromodulation. Then comes to reinforcement learnings. There are several different types of reinforcement learning. For example, dopamine modulated neuro STDP. So dopamine is a biological agent that stays in the brain, and that helps to reinforces some of the learning mechanisms based on a kind of reward functions. So dopamine modulated STDP is that kind of architecture where you have a STDP, but you have a mechanism to enforce some of the actions. And then there is eligibility propagation, which is a very interesting concept.
And all of these are assuming a fixed structure, model structure.
Most of them are, yes,
So,
for
so
fixed,
just the weights are just.
are adapting. So weights are adapting, but you can think of it this way. If the weights are adapting and the weights goes to zero, that connection is lost, right? So basically, you can create, it can evolve towards a different architecture based on the.
You can remove.
Can you add in connection after they've been lost? Because it seems like if you were going to do backpropagation through time,
Yeah.
at least, once the connection weights go to zero, you can never recover it, right?
Here you can,
Okay,
because the weights are continuously increasing and decreasing. If the weights increases, you restore a connection.
so basically, I think what I'm trying to get at is like vanishing and exploding gradient problems. right?
Vanishing and exploding gradient are precisely the problems that we solved using force, and we show that it is, you can solve those problems. You don't need to work on vanishing and exploding gradients yet for spiking neural networks. So as I said, mostly our group focuses on all this blue part. And what we are doing here is we are trying to build the algorithm and the hardware alongside these algorithms. Some of these are used in many different scenarios. For example, we have shown that the force algorithm can be very easy to use for something called dynamical systems. So let's say you have a system that varies over time. So this force algorithm can help you to mimic that system, in the sense that if the input becomes silent over thousands of time steps, we should be able to predict exactly how the model should behave in that time period. So, so force is a very good, and we have demonstrated that. STDP is what we have started with, but we building the hardware for, but we are going beyond that. Neuromodulation, as I said, pattern completion problems that we are using neuromodulation to solve, and eligibility propagation is something that we are using for path planning in robots. So the next outlook I will give is on the application front, and I will not go too much into it, but these are mostly the applications that neuromorphic computing are at least thought of could solve very easily. One of the healthcare or medicine over here, large-scale operations, large-scale optimization problems, security control, and so on and so forth, autonomous vehicles over here. But the most of the research currently is on artificial intelligence, where you are trying to build a kind of intelligent architectures based on or mimic the brain based on spiking principles. So I think I'm running very slow in time, but let me try to see. I have a lot of slides. Okay, so I'll quickly go over a few of the applications that we have shown in the past, and we have done, worked on it. So one of the very famous architecture is called the reservoir architecture or liquid state machine. So a liquid state machine is an architecture where you have a recurrent connector neurons over here, and then you apply a input. So basically you have an input that you excite a reservoir, and then you collect the samples of response from this neuron, and you build a reservoir, build a readout to do certain operations. For example, in this case, you can estimate the heart rate, or in some other cases, you can build certain other things from the readout. So this is an architecture that we have worked on in the past for heart rate estimation problem. Very importantly, what we had to try to do is try to understand the QRS complex. Now, you might say QRS complex is a very known case study, right? With Pan and Tompkins algorithm, you can very easily detect it. However, there are a lot of problematic scenarios. For example, one of the use case that we have dealt with is people with COPD. Okay, their heart rate QRS complex looks extremely different than a normal QRS complex. Even with Pan-Tompkins algorithm, we are not able to get that high accuracy. A person on a treadmill or person on running, the heart rate, the QRS peaks becomes very, very different. So how do you adapt to the situation and then detect those QRS peak is what we worked on in the in our past work. Again, I will, for the interest of time, I'll skip it. This is kind of the architecture that we proposed, where we had a spike encoder followed by spiking neural network, and then the readout unit, which is doing the heart rate estimation. Now, here I wanted to mention one thing that I told you, that you were saying that why do we always need ADCs, analog to digital converter? But think about it this way. You have a ECG meter, which is giving you the electrocardiogram signals that is purely analog in nature. And from that, if you have to use a spiking neural network, you have to convert that particular analog signal into a spike. So basically what you are doing is you are building a spike encoder that takes an analog signal and generates spikes in the end, which then you can feed to a spiking neural network. So there are not just analog to digital converter, but there are many other converters associated in the past. One is the spike converter. And in the past, we have built an analog circuit to do that spike conversion to, to have a ECG signals. This is the QRS peak based on the Pan-Tompkins algorithm, and these are the spikes that are generated using our spike encoder signal. And then these spikes are then used to trigger a spiking neural networks to do the detection algorithm.
So how, okay, so that circuit diagram on the bottom left, that's how those spikes are generated.
These spikes are generated, but after that, that goes to a spiking neural network.
Okay. And the parameters here, the resistance values, I think here. Like,
all this.
yeah.
Yes, those
you,
are.
you have to learn those, or
No. So we used a standard peak detection algorithm,
yeah,
and we converted it into it. But if you can, so the baseline version is from the peak detector. So based on explorations, all those explorations we did, we built the circuit. But later on in the same paper, we have shown that this thing can be completely automated, where you can have certain neurons to do that parameter tuning to.
So you can do like an end-to-end.
End-to-end aspect.
So, oh, sorry, one follow-up. So the spikes that you're showing here, there's like a region where the spikes are on and then they're off.
Exactly.
So how does that work? Is it just like you're
Based on
encoding-
adapt? So basically what we are trying to concentrate here is the region where the ECG signal goes up.
Okay, so it's based on the derivative of the ECG signal, not on-
Some form of it, yes.
So is that the only signal you put into the spike neural network?
This one?
The third one?
Third one, yes.
Then you lose a lot of information, right?
Exactly. We lose, but most of the informations are encoded over here.
I don't think most of the information is encoded there.
So this is not a QRS peak.
Yeah, but you,
Do you really care about this? To
Yeah.
do your heart rate
but
estimation?
then this, so your hand selection, right? That's hand selected.
No,
right?
it's completely end to end. That's why I said the whole thing is end to end. So you have a spiking architecture that captures the ECG signal, convert it into spikes that needed, and then process it. But this is one. This is one for specific purpose, right? So which is the QRS peak. But if you look at heart rate variability, for example, there it is.
I just trying to understand how does it learn? So the selection of those spikes is learned, is not programmed.
This
It's programmed.
it starts with the programming, but then it learns on which region to focus on.
Okay, so there's an initialization.
And
it
then
learns.
you can fine tune it to have a more neural network oriented one.
So it is trying to select the useful information from the source.
Correct. That is what the personalization. So what we are building is a personalization one. This one.
So
will-
basically it's doing the filtering, right?
What is the filter parameters?
I mean, it's not like a traditional filtering, but it's a filtering by converting the.
Yes, but the
representation of
filter,
information.
the important distinction is that the filter parameters changes from person to person. And this is what we are showing, that we don't need to do it person by person, do it as a general case study. You can learn from a person's signal itself and do it accurately. So it's more personalized healthcare you can
Yeah,
consider.
what I'm trying to understand is, so do you have the label? Like, do you have the ground truth?
No, you don't have the ground.
Then how does it know where is the peak?
That's the algorithm learning. That's the learning of the algorithm based on the spike timings that are coming over here.
Yeah, but how? I don't.
Maybe that could lead to a more thorough discussion of the
Yeah,
paper, but I'll
I
just
think more.
skip for the time
helpful.
interest.
So I have a question here. You're showing the spike train. Is that at the initialization, or Or is that after it's personalized to this patient?
So this is for this particular patient, yes. But it will do it for every single patient. So these parameters that you can see are completely programmable for the patient specific, but those
But when you
parameters are
start, you're starting it based on that algorithm up there. So you're running the spike, like a known spike detection algorithm, and you're using that spike
No.
detection algorithm to seed your weights.
to
for-
begin with, yes.
Yeah, okay. And those weights are not what's there, because that like signal regime looks different.
Different,
than
yes.
this. Okay,
Yes.
and this is like what we're seeing at the end.
And
basically.
yes.
Okay, got it.
So how does it learn it then? How does it learn it? What's,
You have two neurons connected with the weight. How does the spike comes, the weight changes, right?
I just want to know, how does it learn the
That's what I'm
weights?
saying.
Yeah, so
The
you know-
STDP is the learning rule, spike timing dependent plasticity. If you have a resistance, you have two neurons, one at one side, the other one is other side.
Okay,
If they are firing at different rate, it learns from the firing times between the two neurons.
Right,
That's
so
it.
that rule that like neurons that fire together, wire together, that's how you learn. This whole thing is learned because you know when the spike hits, the QRS peak hits at the end, right? So you know what the target firing of that end neuron should be,
how
and
do
you
you know?
know what the signal
How do you know
looks
that?
like. Because you know what the QRS complex looks like, right? You
To
know,
begin with,
yeah, you
So
have
that's your ground truth.
you have Hammond Tompkins that will give you the actual.
So that's the
QRS.
ground truth then, right?
Yeah, so like, but yes and no, right? Because
Why?
at the
Why?
end of the, like, you can seed it with that, but then as you like apply it to real patient data, the QRS peaks look different, and basically everything looks different, right? And Hammond Tompkins is unable to actually identify the QRS complex
QRS
properly,
complex.
right? And so the secret sauce that I think is probably on the next slide is how that happens. Because all of them, like the spike dependent, STDP, right? Spike timing
Dependent
dependent plasticity. That's what you're using to train. It's completely unsupervised, so you don't need the answer.
Okay, my question is, so you have like, what's it, Penton?
Hammond Tompkins. Yeah.
That's a new an algorithm based on one model, right? Based on a model that the patient has a very regular shape of
No,
the.
that is a learning mechanism generic for any spiking neural network.
If you go to like hospitals today, that's what they use, right?
Yeah, I know. Like, so that's like the old traditional paradigm.
Mhm.
It's based on the model that this pose has some structure, internal structure in it.
It does, yeah.
You're saying some situations, for example, if this patient has some disease, or if the patient is running or something, its pose does not have this very clear, doesn't have the clear structure. So it's
It's
difficult
there,
to.
but it's not as clear. Yeah.
It is there, but it is hidden.
Yeah.
It is not clear. You cannot extract it.
So why do you think it is there? There probably is some kind of different models to model it. Instead
But
of using
human
this-
can do it, right? Human as a doctor can do it, can find it, right? How? They can recognize that pattern from the ECG, correct?
But then if a doctor can
Do it.
then the
Algorithms-
recurrent neural network.
So the problem is that a doctor can do it, but
Like,
computer algorithms cannot. Hammond Tompkins cannot do it, right? So
you
these
train
classical,
a recurrent neural network, you train an LSD.
I don't know about that one. That
No,
would be possible.
LSTM also we tried, it didn't work. It will never be able to work because as I said, how do you train a LSTM network? It is a completely unsupervised learning. Here it's a completely unsupervised network. Here we are using a learning algorithm, which is inspired from biology.
Hmm.
Just how biology works.
So I have a question here. So if you don't know where the NQRS position is, how do you do the fire together, wire together?
So basically these spikes are coming as an input, correct?
Yes.
So based on these spike timings, you're adjusting it, right?
So
You're
this
adjusting
is the
what?
part I
The
don't,
weights,
so
Okay,
so this
the
is the part
neurons
I'm not
weights.
sure about is when you have your output neuron, it should exhibit the spiking behavior that you're showing in the QRS position.
right?
Thing, right? So how do you know when
No,
that
but
neuron
this
is
is-
supposed to fire?
This is not there. This signal is coming and this is generated completely in an unsupervised manner.
Right, but okay, I guess what I'm asking is, if you don't know what the QRS position is supposed to look like.
Correct.
How do you know
It looks at
that you
the,
will get it correct?
it looks at the signal ups and downs. The ECG
Right.
signals ups and downs. That's it. It
But
looks at.
even if you do that, you would get inaccurate results, right? At the end there, by 2.9, you should also get like a peak detection algorithm might also detect a peak there, and it wouldn't be wrong. So why does, like, how does this algorithm know, oh, that one that happened at 2.675 or
So
whatever is,
these particular characteristics over there, you see,
Mhm.
a dip
Yeah.
and a top is what the algorithm is looking at.
right? But
and
if it's
that-
unsupervised, how does it know that's what it's looking for? That's my question.
No, see, the thing is, what it does is it looks through everything.
Sure.
And tries to separate out the pattern, or you can try to build the architecture in such a way that it separates out this pattern from this pattern.
Yeah.
And then you,
Like, you're saying it's unsupervised.
yes, we don't level it,
You don't give it a ground truth.
right?
You don't give it.
Only the algorithm knows that. So when you have a pure signal, the algorithm knows that a QRS peak looks something like this.
How then?
That
Because-
is how you start with, right? That's what I said, that you start the model in such
Oh,
a
I
way,
see. Okay.
such a way that the model knows that it is expecting a QRS peak where you have a dips and
I
peaks.
see.
Okay,
Okay,
how
so
do you start?
it's initialized with knowledge of what a QRS complex
Complex
looks
looks like.
like. So then.
And
all
then
it's
it's
doing
trying
is
to search that
adapting.
knowledge in a particular signal.
Okay, this makes sense now, kind of.
It's like a labeling mechanism.
Yeah, but
Well, so they initialize
How-
with
how-
the
how-
labeling
yeah,
mechanism,
okay,
and then it
I get
just
that.
containers.
and I don't get that the unsupervised part. If that's true, that's supervised.
It's partially supervised.
It is supervised.
So
Then what is the
It is not
unsupervised?
supervised.
So the
It is not
unsupervised part is when you deploy it and it learns,
In
it
a-
doesn't have the answer.
exactly.
But this is the part I'm confused about. Because I think my question is, okay, let's assume that like you deploy it on a patient.
Okay.
How do you know that it's gonna keep detecting QRS positions at the right place, right?
It may not be. That's
Okay.
that's what you see over here.
So this is just kind of.
I
an
would have got
emergency.
100% accuracy, but you see that there is a deviation in the bits per minute
Mhm.
across different databases.
Yeah, wait, what is MAP?
Mean average percent error.
Okay,
So there is a accuracy loss, but
yeah,
what we are showing is that compared to a conventional architecture, the spiking architecture, the average loss is much lower.
better, okay.
What is it like? If you're going to convert to a convention, you want to convert to a long short-term memory, right? Like an RNN.
It is an RNN architecture. It's a spiking RNN, which
Yeah.
is liquid state machine. It's not a LSTM, but it's a liquid state machine, which is a equivalent of an eco-state network, which is a
I'm just asking, what's the conventional framework you're comparing to?
RNN,
Okay.
which is in the conventional analog domain.
How much better is this than an RNN?
That's what, this is the percentage error that we are showing over here for spiking neural network. And on average, you can see 10 bits per minute, 5 to 10 bits per minute
Wait a minute, okay, so SVDB, ITDB,
are the three databases.
okay, and then each of these.
Bars are for different patients.
Okay, and then the.
Then you have the minimum bits per minute
Okay.
and average bits per minute error.
across-
Error.
Oh, error. okay.
Error,
And this is only for the spiking.
only for the spiking.
Okay.
On average, the RNNs gives 5 to 10 bits per minute
I see. Okay.
error.
Okay. So the error here,
Is 0.6 bits per minute.
yeah, the average is 1.8, 2.6, 3.1. And you're saying for RNN, that's double or triple.
Yes,
Okay.
5 to 10 bits per minute is the average error that we get.
Okay, that's pretty cool. Okay, and this is because the spiking neural network is able to adapt at runtime.
Because we applied a learning mechanism which is unsupervised, and traditional RNNs are not learning. There is no learning in place. You just give a network. That's it. It should do it.
Right, right. Okay. Okay, so there's a little bit of like adaptation happening on the test set here, which could explain this.
Yes.
thing.
So basically, you're doing a shape, a pattern recognition, but it's adaptive.
Right, but that pattern varies from patients to patients. It can have a very low visibility, or it can have absolutely no visibility. If there is no visibility, spiking neural network will also not detect it. And that's where the errors comes from.
So when you compare to the ground truth is labeled by doctors.
By doctors,
Because
yes.
patients-
But how many passes through the data do you have to do?
Single pass.
Single
So we demonstrated this in a European project where we had a patient, put the EEG and we detected immediately.
And even in that short run, it can adapt.
So 30 seconds is where you are adapting, and rest all the time it is just inferring, or however you want to. So this architecture is STDP enabled, right? But you cannot enable STDP throughout the duration, because then your things will be locked. So you have to find a sweet spot of how many seconds of adaptation you want to allow, and then infer. And the first 30 seconds for every patient, if you do it, that's it. You should be able to get a good.
Can you just elaborate a little bit more on the adaptation? How does it adapt?
So you have two neurons. You have a weight connected.
Yeah.
The value of the weight changes based on when these pre and the post neurons are firing. That's the only adaptation. Yeah.
So you can do that for the RNN.
That's the thing. You have to do that for the RNN, but RNN doesn't support it inherently.
Why?
That is a philosophical question I don't want to answer right
Yeah.
now.
I mean, that's just not how RNN work, right?
But you can, so
Basically,
this one you adjust based on the time, right? But RNN maybe you can based on the value.
that's
So no,
Because you're using the
if you-
time for
the
encoding
problem-
the value, right?
Well, no, so the problem if you do that is because an RNN doesn't process data the same way. So if you ever try to modify the weight of an RNN up or down, you would immediately set the weight to either negative infinity or positive infinity.
RNN.
Yeah, because the gradients will explode if you try to like do the fire together, wire together thing like you're doing here. It just doesn't make sense. Like it's not possible to do with an RNN.
see, with RNN, you cannot capture time. How will you capture? You are changing the values with the value of the signals, right? Where is time in that? And spiking neural networks is doing spatiotemporal recognition, which is spatial and temporal.
The whole purpose of RNN is to recognize time.
It doesn't, yeah. So like, yeah,
But when you are doing the learning, I'm saying,
Uh-huh.
how is time coming into picture when you are doing learning? You are doing some mechanism to replicate biology now in analog domain.
yeah. I think you're thinking of RNNs the wrong way. They're not designed to do time-based processing. They're designed to do sequence-based processing.
Mhm.
And those are different because time and sequences are not one-to-one.
Okay, you're saying, so this one, when you do the variations in real time.
No.
Yes,
Well, I mean,
No.
not necessarily.
we are sampling the ECGs
At the same time when you infer.
when we are adapting. So basically, as the ECG signals are fit through into the hardware that we
I
have,
see now.
it's automatically updating
it's not-
and doing.
RNN, you have RNN is that you wait for a second.
That window we don't need it. And this is the reason why this work has gone into Samsung's smartphone, because we don't need any storage into the device.
Yeah,
It's all purely real time. Everything is happening as the signal is passing through.
I see.
No window needed, nothing. You don't need.
But
to
is the
store it.
error decreasing as you go through the training data set?
So, as I said, that there was no training data
Yeah.
set. So what you are doing is you take a patient, you
Yeah, adapt
put him into the front, and you take 30 seconds of, or you keep on feeding.
Right.
For 30 seconds, it will adapt, and after that, it will start developing on its go. If you put it more than 30 seconds, sometimes the results were kind of not that good.
Yeah.
So we found out that, because the thing is, you see the weight changing mechanism, and I showed it before. The weight changing mechanism is, it will continuously change weights as and when the spikes are coming, right? So if you keep on changing weights too often, it will not be very good. So you have to find a sweet spot where you stop the thing and then let it use the current weight, and because
So you treat that as like some kind of a representative data set. The 30 seconds.
No, that 30-second is called personalization time.
Yeah, then
Is
this
that-
data
is that-
set, right?
It's not, no, you cannot call it a data set because I'm not talking about 5 different patients giving 30 seconds. It's a 30-second of the same patient.
Yeah, but for that
One patient, and for that patient, it will
for
start
that
running
patient, it's a representative data set.
data.
Yeah.
Yeah.
and
Wait, wait a minute. So if I had a Samsung phone, I used to have one, and they had this little thing on the back, and then they make you hold it for some time.
Yeah.
That's because it's
That
training
because of
wheels.
exactly where it is adapting to your
That's pretty cool.
thing.
That's dope.
I normally don't call the data set. You can call it data set. I don't mind.
It's
But the
because
data
it's
set
not
is more than one data together. It's just the same patient. It's a
It's like
personalization.
an ensemble.
Which Samsung device does it have it?
I cannot tell you the name, unfortunately.
But
I cannot.
It's probably like an NDA.
It's an NDA.
He's not allowed to tell you.
oh,
Yeah, because I was in the company when.
but I'll be really surprised if it's you using this instead of the hemoglobin detection with optical.
Right now, all these other new techniques came in, like PPGs and all those hemoglobin levels, oxygen saturation level, all those other things came in. But we are talking about 2017, 2018. Okay, at that time, doing a continuous Pan-Tompkins algorithm on a watch will kill the watch in an hour.
Okay, so you're
And-
saying it's not in a Samsung watch now, it was in a Samsung.
At that time, Samsung, when at that time Samsung released their watch, you can go back and check in 2018 which watch got released. I cannot tell you, but you should be able to look into it.
So it's
Yeah.
not used in the property right now.
I don't know, because I left the company.
I'll be surprised if it's not using the hemoglobin detection. Because you can directly detect your hemoglobin like concentration by just using optical device. Like, based on your hemoglobin
yeah,
change
so look,
concentration.
That's the application.
Well,
That's beyond the scope of.
I would also say no, right? Because like you can also detect electrical signals too. But the problem is not detecting the levels, it's identifying what the heart rate is based on those levels. You still need to do this. You still need to do something.
You still need to detect ECG.
Yeah.
And then process it, right? So I'm not talking about the detection part, I'm more
So
processing.
the difference is, you said there's an advantage of not having to wait, but you can process the data, the electric signal live with the spike in your now.
So that window is not needed, window of data storage. Think about it, you have every samples, every EEG or ECG samples. How many bits do you need for each ECG samples, and how many seconds of data you need to store? You can get rid of the entire storage. You cannot have that big storage on smartwatches. The cost will be enormous.
I think other thing you can mention is the 4% energy, right, that is consumed.
Right.
SNM.
So the SNM, the energy consumption is extremely low, and that's what I was saying, that if the test that we ran at that time in Samsung's that particular phone with running Pan-Tompkins algorithm, in 1 hour the battery went down completely of the watch doing the heart rate estimation. Then what we did is we did this for 2-3 days, it was running without any problem. And now they, as I was telling you the other day, right? So we have this neuromorphic hardware which can do the autonomous vehicle, some stuff on autonomous vehicle with two AAA batteries for 6 months, non-stop. And that's where neuromorphic computing is. Okay, so I'll move ahead because there are quite a few more slides to show. This is what we have to do. The second application that we developed is dynamical systems. And again, here, what we did is we used a similar kind of architectures, which is liquid state machine, but this time we have a feedback from the output to the reservoir. And what we did is we tried to follow different type of signals. Basically the idea is to model or mimic a dynamical systems. And we have achieved, again, using a different kind of training called the force training. We were able to actually show that a reservoir network can be trained in a supervised manner as well. Typically, the recurrent network is very difficult to train. And when I say recurrent network, you can call it eco-state network. I'm not talking about LSTM, but eco-state networks are those where you have an input layer, you have a recurrent layer, and you have an output layer. So though that itself is extremely difficult to train. Think about coming a feedback loop from the output to the input. So we have solved that problem using full force mechanism, and we have shown that it can be done. Now, I will not go too much into the full force mechanism, but the whole idea of full force is that what you do is you start with the initial weights and you try to minimize the weights using a recursive least square algorithm. So again, I will not go into the mathematics over here. So what you do is you calculate the error before weight updates, and then error after weight update. And finally, you have three principles. You reduce the weight error during each weight update, and you convert the weight updates, and you train the network using recursive least square. And what we have done is we have started with the original network. We have a reservoir architecture where a second reservoir is introduced only during training. And then once trained, you can get rid of the second reservoir, and this becomes your architecture, which is similar to this. So this is a very interesting work what we did in our algorithmic explorations. There was a hand raised.
Yeah. If you go back to the signal, how do you represent that signal through the output layer? So if Z is a spiking neuron, then how do you just undo the conversion from
Z is the output, which is modeling the input, which is F.
Yeah, so F takes values between -1 and 1.5 or
In this case, yes, but in some cases something else.
so how do you convert the spikes to what encoding do you use, I guess, to go from
Negative, only for the negative part, right?
for both of it, honestly?
Actually, the spike interval. So we have a baseline interval. If it is positive, then the spike interval is greater than that. If it is negative, it is less than that.
Okay.
So
Got it. So you have to devise some kind of
spike device mechanism.
Okay. And then how do you, okay, and the back propagation is the hard part.
There is no back propagation.
Right, or the
This is the algorithm
Right.
we use. I will not have too much time to present this algorithm in details, but you can look into this paper that this year we published in joint conference in neural networks and the full force training.
Yeah.
Okay, so with that, let me shift the gear a little bit towards hardware. Okay. So algorithm is what we talked about. Then we have the whole hardware. So again, this is the biological neuron, but you cannot implement every single thing of a biological neuron. So only a limited amount of components of the biological neurons are usually modeled in spiking neural networks. And we are strictly speaking of the hardware implementation. The first hardware implementation that is proposed was in 1989 by Carver-Meyer, which actually started the field of neuromorphic engineering, where every single architecture that is proposed has some form of this architecture that was proposed before, but it developed quite well from 1889 onwards, and it's still an evolving field. So basically the idea is this. So you have a kind of a block of synapses. So you can, I don't know if you can still see, this is crisscross connections or grid kind of connections. So you can think of these grids, one grid lying horizontally and the other grid lying vertically on top of it. And the cross section between a horizontal and vertical is the synaptic component. So the synaptic weights are in the cross section of each of these neurons. Okay, so initial designs came up with this way. There is a certain set of inputs that are going into this array. There are certain set of outputs that is coming out of this array. So that mimics input axons and output axons. And rest, all the neurons which are in this red block are going and feeding it around themselves. So it's kind of a feedback or loop connections that the neurons are feeding it to itself. Okay, plus you can get an extra input and extra output. And then later on, what researchers went and tried to do is something called the AER encoding. And why that is being done? Typically, these are, you can consider it as a multi-core chip. So when you are talking about a Intel architecture, you have multiple chips, right? And these chips are connected through an interconnect. So think about it. This is one of the code of your system. And this code is connected on a something called network on chip architecture. And this network on chip are digital in nature. So what you have to do, you have these spikes, all these analog spikes coming out over here, right? You have to somehow convert that into a digital format so that it can be transmitted across the network on chip to another one. So they came up with this formatting called AER, which stands for address event representation. So for every event, it represents it as a packet with a header only. There is no payload, only the header. And the header contains the address of the neuron where this neuron's output is going to go. So let's say this neuron is connected to, in your actual circuit, actual application, a neuron like this is connected to another neuron somewhere else. So then whenever this neuron will fire, the AER encoding will insert the address of the neuron where this spike has to go. And this address over here is then broadcasted across the network. And whichever core has the neuron ID will pick up the packet and give it as a convert it back into spike and give it. So it's a lot of conversion happening on a scale. So at one level, you have the analog neurons generating spikes, which is purely in an analog domain. That is converted into a digital packet that is being routed across the network on chip. And then once the spike reaches the destination, it is converted back into an analog spike, analog voltage, and given to the particular neuron. So that was why all the analog to digital conversion comes in. And there are some accuracy loss there as well in converting a spike into the digital.
So this may be a bit of a new question, but at the end of your spiking neural network, you
Right.
have a direct delta function, which is either on or off, right? So isn't that already digital? Like the delta function at the end is
Yes,
either, yeah,
one or it's a 0 or 1.
yeah.
But where do you send it?
Just have
Or
that
who do you
first.
send it to?
So
Who should receive it?
can't you just put like a packet header around it and call it?
That
a
is
bit?
exactly what.
Okay. Got it.
It's just a header, nothing else. That's why I said that it's a packet with just a header.
Okay, got it.
And the header information is
Oh, right, because if it's a 0, you don't send anything. anyway.
exactly. If it is
So-
a 0, you don't send anything. If it is a 1, you send it.
Got it. Okay.
So this is kind of where the neuromorphic hardwares are started with. In 1993, only IBM and General Vision and some part of CERN were developing these spiking neural networks. Then it was picked up by Human Brain Project, where I started working on, and then it started with other partners, Intel, IBM, and many other people are now working on developing this neuromorphic hardware. And these are kind of the chips, different chips that are being proposed so far. And in terms of the number of neurons that you can see over here. So this circulating thing is Spinnaker from University of Manchester, one of the most famous neuromorphic hardware. This is IBM's True North, which is also very important ones. But all this you can see, the number of neurons is 1 million. Now, 1 million neuron is not just 1 million neuron. It's 1 million neuron with 10 million synapses. If you have a fully connected, it's 1 million times 1 million connections, but you don't have a fully connected neuron. Usually it's 10 million. So 1 million neurons with 10 million synapses is this architecture. And later on at IMEC, we developed something very close to human brain, which is neuron 3, where we had close to 1 billion neuron in the architecture and 10 billion synapses in one single chip. Yes.
If I want to send a signal from the furthest point to the diagonal point, how
Yeah.
fast
How fast it is
Yeah.
in terms of
time?
everything is happening in terms of milliseconds. So it is not
Yeah.
that different. So 1.1 millisecond maybe. If you send it at X millisecond, X.1 millisecond will get it. It's not that.
Okay, so around the magnitude of 1.1 millisecond.
What can happen?
No, 0.1 millisecond.
0.1
1
millisecond. It could be a little bit longer depending on what kind of interconnect are being used. But if you, for example, use photonics interconnect, it will be super fast. Everything will be extremely. Now, you might wonder,
Yeah.
what is its problem? What does it matter how much time it takes?
No,
Okay.
I'm wondering which is the most time-consuming part. Is this the ADC conversion or it is a state?
The time consuming part is always the interconnect.
Interconnect.
Because
not
this
the time
interconnect-
multiplexed.
Exactly. So you are sending one spike from the farthest corner to the corner. I agree. But what if everyone tried to
Yeah,
send
I know,
everything?
I know, yeah.
So you-
So basically the limiting factors here is that the maximum number of synapses is very difficult to make.
Excellent.
Too many wires.
So you cannot have too many wires.
Okay.
So what you do is you have one wire which
Yeah,
you
it's
time
multiplex.
multiplex between the cores.
Wait a minute, why do we care though? Because like,
Can you hold on to that question? I will show you why we care actually.
okay,
We'll show how accuracy can be completely devastating.
well,
If you
if you design your connection, if you say started off with everything connected to everything, right?
you
Or-
cannot build that hardware.
okay, so with a maximum number of connections, right? Wouldn't the time delay, if it's a constant time delay, just become part of the signal?
Yes, but it is not a constant time delay
Oh,
because you have to think about arbitration, right?
right.
So everyone trying to send it, you have to have a round robin fashion. If one person sends too many spikes, that's it. You will be always giving the priority.
So
to the-
biological brains avoid this because you get constant time.
Exactly. So biological brain, what it does.
It is mostly, right? Your synapses are right next to each other.
Well,
And the time
no.
delays will
It's
always be
it's not true. Synapses are not always next to each other. It has long connection.
Yeah,
with
it's really
axons,
long connection.
right, but even if you send it through an axon, the transmission time from one end of the axon to the other one is
It's
basically
milliseconds.
constant.
It's still milliseconds.
But it doesn't matter how long it is, as long as it doesn't change.
I think it
Because
changes.
It changes, and
Oh.
that's
Oh.
everything changes. You know, so but here we might have a different problem because here we are not exactly replicating biology, but we are trying to
Inspiration.
put together an application inspired from we're using machine learning model inspired from biology. So the application performance might completely degrade. Okay, if it matters, yes, it is a problem. If it doesn't matter, it's not a problem. So we'll show you that. Okay, but important things to know is that with 1 billion neurons, the things get really, really complicated. And 1 million neurons, 10 billion synapses is the energy consumption can be exceptionally high. So we have to be very, very careful. And in our recent work, we have shown that out of all the energy consumption of a neuromorphic hardware, the communication constitute almost 60% of the energy. 40% of the energy is consumed in the computations of the neurons. 60% is on the interconnect. So these are the key requirements to make a hardware. I just wanted to let everyone know that you need to have in-memory computing, parallelism, nonlinearity, asynchronicity, sparsity, continuous learning, probabilistic computing, scalability, and analog. Not every hardware does that, but you have to mimic these principles to the best you can. That's become neuromorphic computing. Now, the other thing that I wanted to mention over here is that all these neuromorphic developments are happening now in the recent years. In-memory computing is coming into, but throughout the last 10 years, mostly people focused on number 9, which is analog computations. Digital chips are extremely power consuming because of the clock signals. The clock signals can be lead to an interpart. Analog asynchronous circuits are way more efficient that way. And no one really works on continuous learning or online learning. And yeah, that's where we were working. So for those of you who are wondering, this circuit, this was the basic circuit. This is the actual circuit that you will see each neuron. This is each neuron circuit. Okay?
Wait, so in this diagram, everything with a letter is a parameter you have to train.
Everything with a letter are the neurons or the parameters that you can change. But usually what people do is you set the parameter one time and replicate it everywhere.
Okay, so you just leave it and then,
leave it in.
so how many of these do you actually train?
1 billion of these.
No, like how many parameters in this neuron?
Oh, no one has ever tried training individual neurons with a parameter. People come up with a set of parameters, everyone uses that parameter. And those set of parameters are decided based on thorough analysis of how this neuron will behave, mimic the actual spike dynamics.
Wow, okay.
They come up with a parameter and that's it. They
And
give
you
it,
just
this
leave
is the parameter, use it in your design. That's it.
Okay, and then, so if I'm like adapting this neuron during inference time, what am I changing?
Yeah, you are not changing anything on the neuron.
Literally nothing.
Nothing changing.
Oh,
Even
it's
in-
just the connection weight.
Yes, you are
All
not
of the
changing
neurons are the
anything.
exact same. The only thing you're changing is the connection weight.
How many parameters you can see? Quite a lot.
Yeah,
1 billion of them multiplied by that.
I mean,
That
yeah,
many parameters. It's almost impossible to train.
that's pretty gross. Yeah.
Plus, Not only that, you have to also think about the parameters of the weights. So all this is the huge size spiking neural network.
So basically, like, you're doing the same thing that you do in a neural network. You're just training the weights.
Exactly.
You're just considering this as like a really interesting activation function.
Yes. Yeah, actually, you did it
exactly
very
what I said.
nicely. Yes, you put it very nicely. It's a very interesting activation function. That's it.
Okay,
You take it like that and move forward with it.
got it. Okay.
I usually take it like that. So
Okay.
I never bothered to change any of these parameters. It's too time consuming, plus half of the parameters. If you set, you will see that outputs are
It
either
won't
tied to
work.
0. It doesn't work. Yeah.
Yeah. Wow.
So this is one neuron implementation, which is the leaky integrated and fire neuron. There are a whole bunch of other type of neurons. There is something called Izekevich neuron, which is a special type of neuron with a special type of spike dynamics. So every neuron has a spike dynamics that you have to mimic using an architecture. Anyway, so moving forward, so one of the interesting things that you can do is implement a crossbar kind of hardware where you have this horizontal bars, as I was mentioning, which propagates voltage. Okay, and think about it here. We use a little bit of circuit theory, voltage, and this is the weight, voltage, but the weights are programmed as conductance. Voltage multiplied by conductance is current. So you get a current, and parallelly, every current is accumulating, Kirchhoff's current law. The architecture becomes completely parallel.
How do you isolate the effects of different? Oh, right, it doesn't matter.
It doesn't matter
Got it. Yeah.
because all you are doing is summation xi wi. Xi is voltage, wi is conductance, xi and wi is current, and current gets automatically added in parallel.
Got it. Oh, that's nifty.
And think about it, this is just one, right? You can have, so this set of weights is computing on this side. This set of weights will compute current on this side. This set of weights will compute. So it's entire matrix multiplication happening all in parallel.
And this is the reason why you have to group things in cores, because you can't separate out any of the effects.
Fantastic. There we go.
Okay.
And then all these weights can be any exotic materials like phase change memory, resistograms. All these are novel materials that you can use to build this transconductance over here, so that current can flow through them, multiply. So you don't have any CMOS components anymore. Of course, CMOS are there to build your neurons, but synaptic weights are all in exotic memories like this. So this is all about neuromorphic computing, and we have built our something called microbrain in our previous work, where we have implemented each core over here is a 3-layer architecture. Instead of a crossbar, now we built a 3-layer architecture, and using that we can implement any different types of computations like convolution, pooling, concatenation, residual computations, and so on and so forth. Plus, we can make this course big and little. So think about it, ARM came up with the big little architecture. Why was it so popular? Because some cores can do something else, some cores can do some little computations, but more energy efficient. We built an architecture where all the cores are either big, little, different shapes, so that you can map smaller components, bigger components together in this kind of architectures. I don't know how much time I have, Rahul.
Oh, it's very interesting to know. If people have to leave, you can.
So this is our microbrain design in nanojoules, the energy consumption as compared to all the other designs that I proposed. The last column is Loihi, which is Intel's. So you can see the 85,052 or 8552 is the nanojoule that is consumed for your MNIST, whereas microbrain consumes only 308, and microbrain is a digital design. The rest, all the designs are analog. With analog, of course, you will get lower energy. But even with digital, we were able to achieve a very low energy consumption. And with MNIST, our accuracy is only 91.7%, very straight up.
So microbrain has that
3-layer
crossbar
architecture.
layer.
No, it's not a crossbar. That is a very different from all the other. It is a 3-layer architecture. layer 1, layer 2, layer 3. And how we change the connections, you can implement convolution, pooling, and many other things.
Here's a question. If you can do matrix multiplications basically instantly, why don't we do that everywhere? Like why, like
That
you
is-
need to do that for
Everything,
CNNs and everything else too. If
exactly.
you can do it at constant time, why?
Yes,
don't we
but
do it?
not all the operations of a CNN are matrix multiplication based.
Right.
So only for the convolutions you can use it. But there are other special functions, right? But we have shown using that architecture, we can implement both convolutions and special function. So you don't need a cross, because crossbars are only for
You
convolutions.
can do one thing.
And who was asking me about FPGA?
Oh, that was
That is our FPGA design.
Ah.
The same microbrain we have implemented on a FPGA, and yeah.
So AER in is the
Address event representation in, which is
Slash
this header file coming in, and then AER out is the way going on. And the next few slides, we have modified a lot. For example, or we have moved away from the conventional network on chip, because conventional network on chip itself, for each router, you will see a lot of, it's a storage. So every packet is coming, you're storing it into a buffer and then forwarding it to another port. So because see, each router over here can have east, west, north, south direction, right? So whenever a packet is coming, you can either route it to the east direction, west direction, north or south direction, depending on where your destination is, right? So you have to have all those information stored in the router to understand where you have to do it. But we have moved away from network on chip, and we have implemented something called segmented bus, where a bus is, right? It's a single bus where multiple things can communicate, but you have to arbitrate. But once you have allocated the one particular core connecting to another, the bus becomes useless because you cannot use the bus for any other purposes. So what we did is we segmented the bus such that multiple parallel connections can do it. Plus, it doesn't have, the routers are very simple and not this kind of routers with ginormous structures.
So in this case, C3 doesn't communicate to anything. Is that because it's also connected to a bunch of other buses?
Other buses, but C3 can technically connect to another one also.
Right.
But we are not showing the connection here, but I'm saying that using segmented bus, you can support multiple parallel connections to build up the hardware.
Got it.
Okay, so this is the same thing. And as I said, our switch is something like this. It's a very simple switch. Together with IMEC, we designed that switch, and we designed that entire architecture on hardware, and we got very good results. And building on top of it is where we talked about on-chip learning. Remember, we talked about how you can do STDP-based learning. So our architecture in that case was each tile will have the microbrains, which are written as NPU, which is neural processing units, and OLU, which is the on-chip learning unit. So this is the learning hardware that you can also have inside each tile. So our design, which was published, which will be published in January, is called Echelon, which is a many-core hardware for on-chip learning. So that's more or less on the hardware side. I want to give you a high-level idea maybe on the software side, so that just to make the story complete, and then maybe talk a few more slides on the core design, so that will be useful. So this should be known to everyone, right? So every computing, whether it's a neuromorphic computing or it's a von Neumann computing, always have three typical layers of abstraction. You have the hardware, you have the system software, and you have the application, which is the algorithms and everything. Same thing here in neuromorphic hardware also, we have three types of abstractions: hardware, application, and system software, except no one works on system software. We are probably one of the few groups that works on system software, okay? So which we interfaces between the application and the hardware. That's the hardware software interface coming in, right? So you have an application, how do you map that application onto the hardware? We have used typically like a compiler. We have designed a compiler which is called MLIR, machine learning intermediate representation, which can take any front end. That means you can write your Python code in Keras with the flow, in PyTorch, in C++, R. It will have an intermediate representation, and then you can custom that representation into any type of hardware like Echelon, Loihi, Spinnaker, any type of hardware. So this one representation here allows us to interface with many different front ends, just like your operating system, right? Your operating system you can write a code in C. You can write a code in C++ or in Python. Same thing we are doing over here. You can write it in any language you want, and then depending on where you are targeting it, it will generate the custom code for those specific hardware. Just like whether you have an Intel hardware or AMD hardware, it will automatically generate those kind of architectures. And for that, what we usually do is we take a map and then we represent it as a data flow representation, and then we have to cluster it and map it. And there is where I wanted to show you something very interesting. So let's say that you have designed this algorithm that need to be mapped to the hardware. Now the hardware looks something like this, right? In some form, you have hierarchical interconnect. What I'm showing you over here is, let me explain a little bit what I'm showing over here. Let's say that I have 3 input and 1 output neuron. So 3 neurons are connected and 1 output neuron are connected. And let's say that the input neurons are connected somewhere in some core and the output neuron is somewhere else.
One conference.
That's right, just
So what is happening over here is, observe the first picture over here. The first picture shows the time where the input spikes are, and it generated an output spike based on that threshold crossing. Okay. The second picture, what happened is there is an ISI distortion. That means the spike got delayed somehow. Can happen, right? Because you are using a shared interconnect. Think logically from the perspective of the membrane potential. You have membrane potential keep on increasing. All of a sudden, you didn't get a spike. It starts falling out. At later point, when you get the spike, maybe it is so low that it might not fire.
Got it.
You see, a spike was expected in the application. In the hardware, you might not receive a spike. What does that mean? You are looking at an accuracy which is like 95%. When you map the algorithm onto the hardware, you might get 85%.
So
That's a very dangerous part about the neuromorphic computing.
So couldn't you avoid this by maintaining a clock? Like,
Then you increase the power consumption.
right. Okay.
So what we did is we tried to do a I forgot, it was a some filtering operation we implemented using spiking neural networks. And this is without ISI distortion, and this is with ISI distortion. You can see the difference in the image quality. Okay. Yeah, so it can get very bad results. And with MNIST, we started with an application level simulation with 98% accuracy. When we mapped into hardware in an incorrect way, we lead to 68% accuracy. It's a lot of loss.
So what hardware were you mapping that on?
That we are mapping it on a hardware called DNAPS, which is from Zurich. So that is a spiking hardware with 4 cores, but with a time multiplexed interconnect. Actually 8 cores. So basically you have 2 groups of cores, and then you have a interconnect between them. And that interconnect was time multiplexing, and our accuracy went down completely.
That's another question.
It goes back to your 1.1 millisecond, right?
Yeah.
Yeah.
So 1.1 millisecond that's what, some application can tolerate that much. So you might not have any problem. Some application cannot tolerate, and then you get a loss.
So, how long do you have to hold an input to get a reading?
Excellent question. Usually 10 to 15 seconds
Okay.
per image.
Okay. So
Basically, you have to generate 10 to 15 seconds worth of spike.
yeah, and then once you do that, do you get like a gradual result? Like at the beginning, do you get like a very weak result?
Weak
and
result,
then
and
strengthen?
slowly it strengthens out.
Okay.
But again, it becomes weak because you will take out the image, right? So you present the image and then you take it out.
So let's say you're doing video, right? Let's say you're trying to segment video or do something, or
Right.
do I need to hold only the first frame for 15 seconds and then just play the whole thing real time?
No. So basically, think about it this way. So you have image. So that is a very interesting point. So basically what happens is in that case, you lose the real-time aspect a little bit.
Okay,
So every image need to be held for a few seconds.
got it, okay.
Okay. 15 again, that depends on what frequency or how fast you are running your neurons and synapses. 1 millisecond, right?
Right.
If you're running it at 1 millisecond, I would say that 30 to 40 milliseconds is what you have to hold it for.
Okay.
If you're running it at a more slower rate, you have to put it more. So it's a accuracy versus real time or energy versus real time exploration that you can do.
But is there some relationship between like the continuity of, so like if I take one frame and then I take the next frame,
Excellent.
they're almost continuous, so I can just
Play
switch
it.
easily.
Yeah,
But if I say, okay, I'm only gonna take these pictures at 10 hertz,
yeah,
and there's
but you
gonna
have
be a
to
lot
clear.
more discontinuity, do I still need to hold the image? for-
Right. So what you can look it into this way. Okay. Either you can play your video at a very slow rate.
Yeah.
Right. Every frame, instead of the actual frame rate, you can play it at 40 milliseconds per frame or something. Right.
Yeah.
Or what you can do is you can drop frames. So basically present it and then you don't show anything. Or you keep on holding that while you drop up the other frames, and then
you show
whenever the next frame comes, show it. That also
That
works.
works, okay, cool. And
Because-
you only have to hold it for the same 30 or 40 milliseconds, it's
Yeah.
fine. So you basically need to hold static images for 10 to 15 seconds because you just need the initialization buffer to build.
Not only that, think about it, all the neuron parameters. It
Right.
depends on the neuron parameters because the neuron potential has to go up and then go
So
higher and all
There's
those
like
things.
some kind of equilibrium state that you have to hit, and once you hit it, you can do whatever basically.
Yes.
Or like, I mean, not whatever.
Not
but-
whatever, but yeah, most of the stuff. Yeah.
Okay.
So it is a very intriguing relationship between what the neuron parameters are and how the mechanism. Again, if you
So
think
if
about
were
it,
to tune the parameters, you could maybe get it to where it reaches an equilibrium state much faster, and so you don't have to.
yes, but then you will sacrifice on energy.
Right. Okay.
So that's why I said it's a very much energy compromise that you can play on, but the space is enormous.
Yeah.
You can fine tune anything and you can craft your own model and that's where the design, co-design aspects will come in, where you can co-design the hardware and the algorithm together in a both top-down and a bottom-up manner.
How expensive is it to simulate a neuron? Because there's a lot of components there.
When you say expensive, is it computationally
Yeah.
expensive you are talking about? Yes. So basically there are a lot of good simulators available that you can use to simulate, and some of them are even GPU accelerated. So it is not that difficult.
Yeah.
Depends on how large you are simulating. If it is 10-15 neurons, you can do it on your laptop. It's not a problem. Even with 1 million neurons, you can easily run on your laptop. It's not a big deal. The moment you cross 1 million, probably 10 million onwards, you'll see that you need a GPU. Otherwise, it's extremely slow.
Okay, so if I wanted to run like VGG or like ImageNet or something, or ImageNet is a data set. If I wanted to run like, some ImageNet classifier, I would not be able to do that at a reasonable rate on a computer without hardware acceleration.
No,
It's just not good for it.
not good.
I mean, you use a GPU.
You will use GPU.
Yeah.
Even if you do that though.
No, it's
No,
fine.
in
I think it's
GPU you
fine.
can.
Oh, it's fine with the GPU.
GPU,
It's-
yeah.
Okay.
So that's what.
The only problem is the connection. The interconnection.
But again, these are all simulations. In simulations, you don't have
Yeah, it
that
doesn't
delay.
matter. Yeah.
You don't have that delay
You can just
information.
assume it's perfect.
Exactly. So what we have built in our group, and I will show you later on, is something called a hardware simulator, hardware software co-simulator. That means you can either simulate it on the software or you can simulate it on a hardware model. Not exactly the hardware, but all the components and latencies of the hardware are there.
Right.
So basically, you can exactly predict what your application accuracy is going to be when you map it onto the hardware.
Got it. Okay, so you're simulating the whole hardware thing with all the interconnects. and everything.
Yes.
Got it.
With all the interconnections and everything. So you can literally predict what is your accuracy.
Yeah.
I'm wondering, have anyone tried an architecture of using like a hierarchy of neurons? Instead of connecting every neuron to every neuron,
Multi-compartment neuron, you mean?
yeah, we can have a neighborhood of neurons.
Yes,
where
it's
they
a
are-
multi-compartment neuron. Yes, people have tried it. And we also do that. So basically what happens is you have a clusters where you have
which is faster to communicate inside the cluster.
So is there like, there's probably work on this, but like ways to optimize the connections between because like you have a bunch of these neuron centers.
Right.
you want to minimize the physical distance on chip between all of them. that are
That's
connected.
what we do.
Okay.
What we do is through software, we configure the entire interconnect in such a way that those cores that are communicating the most are placed in the near way.
Got it, okay.
Or
So
those,
it's
exactly. So all those explorations we do.
Yeah. So you run that optimize, that's what you're talking about with the co-design, that's your joint optimization. Got it, okay. That's cool.
Any other questions?
Wait, so what is this thing on these plots on the right?
Oh, these plots, we are showing that how we could minimize the number of spikes on the interconnect. So basically, that's what another thing I was showing you over here. So let's say that you have neurons. These circles are the neurons. You can cluster it also intelligently such that, you know, the number of intercluster spikes are minimized. That way you are actually reducing the number of, because remember, each cluster is going on a core. That means intercluster communication is using the interconnect, right? So if you can minimize the number of intercluster spikes, you're actually minimizing the chances of losses, right? So that is exactly what we do using particle swarm optimization, where we try to find out the sets such that the cut of the graph, we cut it in such a way that, the weight is minimized.
Can you train it to use less intercore connection?
Sorry?
Can you train it online to use less intercore connection?
Online training, online we do some remapping based on if we see that between two cores there are too much communication happening.
Yeah, but that's with the heuristic. If I'm just saying that if there exists a unsupervised training
Heuristic.
method.
Yeah,
that
but
can-
these are very heavy. Yeah, particle swarm optimization or genetic algorithms are too heavy to run on online.
Yeah, I know. Like these are all just side stuff.
Right, but
There could be-
technically, yeah, there could be some way where if you can find a way where you can analyze everything online and unsupervisedly learn how to place
Yeah,
these
yeah.
clusters, that would be very interesting as well. The thing is, clusters are formed beforehand because you have to map it on through the hardware. So you in the compilation stage itself, you have to look at the map, see how much are these spikes should be based on your data sets or training data set. And then you have to do these cuts so that the cost is minimized, and then each of these clusters can then go into one of the hardware. Okay. But that's not it. Think about it. You have 3 clusters now. This is a network. How do you place these 3 clusters? I mean, this is a very obvious solution I'm showing because there is only 3 clusters. So you have one, you can place it A, B, C like this on the diagonals, or you can place it A, B, C over here, and each will lead to a different results. But this is a very simple example. Think about hundreds of cores and hundreds of places to put. It's not a very trivial solution to find the best place where you can put the
How
clusters.
long does that optimization take to run?
A few hours.
Yeah.
Few hours for Alex.
Yeah.
But it is all done compile time. Once you are done, you can map it. So this brings us to this another problem, and that is the side research that I was telling you. So we know these crossbars can build using these non-volatile memory elements, right? But the problem is, I don't know how many of you are aware of the circuit stuff, but if you look at a crossbars, there are a whole lot of parasitic components. These are components that we don't account for usually. And these parasitic components are these capacitors, line-to-line capacitors, how close you are placing the wires and all these things. Those parasitic components can lead to a lot of variations in temperature. So basically what it means, I'm showing here is a 128 cross 128 crossbar, and I'm showing the temperature profile between which connections you are using and how temperature can fluctuate. So if you are using somewhere over here connections, temperature is not that bad. But if you are using somewhere here, the temperature can be very bad. Current wise, this is very high current. That means if you give a spike over here, you will immediately get a response over here. But current will take longer time to propagate. So it's a speed versus temperature trade-off. You have a higher temperature over here, but you have a higher speed to get a spike over here. So
shouldn't they have similar problems in normal chip design? Like how do they solve it in like a regular, like an Intel chip? like a
They do timing closures and all those extra other features that digital design offers.
got it,
We are talking about analog.
got it.
Analogs are too dangerous to deal with. So as I said, synapses at the bottom of a crossbar are faster to access, but results in high temperature, whereas at the top right corner, which is at those corners, are slower to access but generate lower temperature. So you now talk about a trade-off between speed and temperature.
Do you do like thermal throttling or anything?
So we use something called hotspots to find out what are the components where the temperatures are higher. So for example, here, if you are accessing this, that means if a spike is coming and hitting this particular synapse too often, it can generate a temperature that can leak to its surrounding. But then if you think logically from the phase change memory perspective, if the temperature is too high, its resistance state can change. So how many of you have heard about row hammer problem? So row hammer is a very big security problem in any computer, by the way, just letting you know, you should research it a lot. So if you try to access the memory too often, the surrounding part of the memory can lose its data. We are working on something called thermal hammer, where you can actually hit one of the cells too hard, the temperature will leak to its surrounding cells and destroy their completely architecture.
So this is a somewhat related question. You get like these output voltages on these rails, but how do you actually, where are the neurons?
The neurons are sitting at the edge. One presynaptic neurons are on the left-hand side, postsynaptic neurons are on the bottom side
Okay, so they exist physically off core, off
Yeah,
the rail.
of the rails, yes. So here is what I was showing.
Oh, okay.
These are the neurons and the connections. You can either map the neurons like this so that it uses this connection, or you can map it like this. Which one would you choose? It's a problem that we are trying to solve. If you choose this one, it is faster, but it will lead to higher temperature. But if you choose this one, it is slower, but lower temperature.
So does the speed,
Matters.
the speed does matter.
Yes.
So I guess then here's the follow-on question. When you train these online, do you see like, or when you deploy them and you refine the training, do you see like a general pattern where you see the devaluing of weights in the top right?
We
Okay.
do see that variation.
That
And
makes
if you do not model it in the application level, you might get different result. And that's where our hardware software
You need to do
simulator,
the core optimization. but it
Exactly.
won't work here, yeah.
that is where neuromorphic computing is so much powerful about the core design. And just I will show only this slide because the entire runtime is very different. This is our Neuro Explorer framework, which can do software hardware optimizations at the same time. Simultaneously, it can generate your neural architecture onto FPGA, like automatically generate architectures onto FPGA. Okay, I'll not go too much details about it because there is a whole bunch of stuff associated. So I'll just quickly move on to the co-design aspect and then call it a.
How long does it take to build this hardware? Like, let's say you generate a new hardware design. How long will it take for you to get the chip that does the thing?
On FPGA,
Yeah.
my project that currently I'm running, and I think I told you, right? I got a significant amount of funding from Accenture to make it within 15 to 20 minutes or 30 minutes.
Oh,
at
that's
max.
really good.
Yes.
Okay. And do you see like performance degradation when you move from like or does an FPGA degrade performance as compared to like custom built silicon?
Yes.
Yes, that's
And how much of a difference does it
A
make?
lot.
Okay.
So
So-
we prototype the same design on FPGA, and we prototype the same design on a pure, or we put a design on ASIC or analog design. There was a significant amount of energy related difference.
Mhm.
Almost, I would say that 20 to 30% energy reduction we can see as compared to FPGA.
So does an FPGA actually, like, does implementing it on an FPGA actually give you anything then?
Yes, it is. I'll tell you why.
Mhm.
If you are running an application and you want to see how much performance you get, performance, accuracies and number, and roughly how much energy efficiency you are expecting as compared to running on a CPU or a GPU,
You need one, okay.
at least prototyping wise, it makes easier,
And
right?
then how long does it take for you to go from an FPGA design to an ASIC?
6 months.
Okay.
9 months.
Okay. So you can get
Depends.
from, like, you can get from general purpose silicon to FPGA quickly, relatively quickly, like in 15 to
So
30 minutes.
basically, we are not there yet, but the idea is like that. So a user who is writing an application should be able to generate a FPGA design in 30 minutes by push of a button.
Got it.
That's the project.
How long does it take now?
Now it's a lot of hand working.
Oh,
now we still have to do a lot of hand. So everything has to be automated. That's the project about.
Okay.
Okay, so with that, I just wanted to go quickly go into the co-design part because that is another interesting. So as I was telling you, right? So there is a whole bunch of learning algorithms that you can see over here, right? So backpropagation and its variants, STDP and its variants, force we have done, EPROPs we have done, and many other new biologically inspired learning algorithms that are coming on a very regular basis nowadays. And then you have all these different type of materials. You have pure CMOS implementations, FPGA implementations, CMOS and emerging memory, CMOS and future memories like organic memories. So all these things. So all you can do is a co-design where you have all the different stacks working together and you are optimizing it jointly, which I'm showing over here. So you have the application level over here. You have the hardware level. Typically, this is what exists on today's slide. Application, hardware, device, and technology, all working together in a loop to do the optimization. But what we have shown is that this is not it. The system software plays a lot bigger role. You can mitigate a lot of hardware problems at the system software level. You don't have to optimize it for the application and algorithm. I'll give you a quick example. Think about it, the phase change memories. These are very much unreliable memories. That means that you run it one time, you get a behavior. You run it the second time, you'll get a very different behavior. So this variability is a big thing. So you can do something. You can do a circuit level optimizations to reduce variability, which typically comes at a cost of extra hardware. Or you can do an algorithm level variability reduction, which comes at a cost of loose application. But we have shown that actually system software can tackle all these things very easily. So why compromise on the hardware and the software when you can compromise or can optimize the system software? And that's where we build the system software inside the loop. So now we have application, software, hardware, and technology all working together to do optimizations. And we can do top-down or we can bottom-up. That means some application features can lead to different new device technology optimizations. Some of device technology feature can be incorporated at the application level to do new application development. So this is where we are going towards. I'll end it over here. So these are some of the programs that I'm running at Drexel. And sorry,
No, that
instead of
was-
60, I went to almost 2 hours. Huh?
No, that's good. That's our informal discussion here anyway, so.